A simple oscillator like this is one of those fundamental circuits that pays dividends to understand. It doesn't rely on a 555 timer. You get a practical design experience, and the end result is a surprisingly versatile circuit. I like to see examples like this one in electronics lessons just a little bit after the introduction of bijunction transistors because it's a great way to internalize some of the weird, almost magical ways transistors work, and it would be super cool to see what students do and where they go with this particular knowledge. Any oscillator needs some type of energy storage that we can manipulate up and down. We'll start with the trusty RC circuit, one resistor, one capacitor. Measuring the voltage across the capacitor gets us this nice exponential increase as expected. For oscillation, though, we're going to need to periodically discharge this energy once the capacitor voltage hits a certain upper threshold. We'll create that upper threshold with a voltage divider over here, and we're going to make it a nice round 10 volts just because we can. We add a PNP transistor acting as a gate that will open once the emitter voltage gets high enough, just high enough above the voltage threshold to open and discharge the capacitor. We could discharge the capacitor by tying the collector directly to ground, but it won't oscillate. As soon as the capacitor drops a teensy bit of voltage, the transistor will return to cutoff mode, and the capacitor will return to charging mode. Then instantly discharge a bit again, then recharge a bit again, and back and forth, which gives us this steady voltage right at the threshold voltage of the emitter. What we need is another transistor to hold that PNP transistor gate open. To do this, we'll add an NPN transistor here. So, when the capacitor reaches that appropriate threshold voltage, the PNP transistor saturates. This quickly saturates the NPN transistor, shorting this node and bringing it down from 10 volts to 0-ish volts. And then, once it's at nearly 0 volts, it's low enough that the PNP transistor will stay saturated and let current flow for much longer until the capacitor has discharged practically down to 0. This then cuts off the PNP transistor, which cuts off the NPN transistor. The threshold voltage jumps back up to 10 volts and we resume charging. So, are we all good? Is that our oscillator? I'm leading you on. It totally isn't. If you look at the path that the current has to take in order to discharge, you'll see that it's pumping almost all of that current through the base emitter junction of the NPN transistor, and that's bad. Here's a simulation in LT-Spice of the current flowing through that base emitter junction. Yes, those are kiloamps that it is trying to push. The base emitter junction isn't designed to reliably discharge current at all, and it will put considerable strain on the transistor and your power supply. So this isn't an oscillator yet, it's just a fire hazard. We have to provide an alternate path for current to flow while we're discharging the capacitor. So let's add a diode between the NPN collector and the capacitor. So current will only flow through this diode during discharge. To predict what happens next, we're going to need to think about the voltage drop of the diode itself and the base emitter semiconductor in the PNP transistor. If the diode's voltage drop is smaller than the PNP base emitter voltage drop, then we're never going to trigger the NPN transistor. Instead, current will start to flow through the diode prematurely, and we will hover right below the capacitor discharge threshold voltage that we want. We'll just stay at that level forever. And there are lots of potential ways to work around this. I'm going to take our voltage divider and divide it even more. We're not going to change the threshold voltage that activates the PNP transistor, but we can raise the voltage that activates the diode. So by tying the diode to this upper node, which has a voltage of 11 volts, and tying the PNP base to this lower node, we ensure that current is going to start flowing through the PNP transistor before current starts to flow through the diode. And by tying the NPN collector to that upper node, we're shorting that part of it, ensuring that current flows through the diode and not the base emitter junction of the NPN transistor. There's also the potential that the diode voltage drop is greater than the voltage drop of the PNP base emitter. In this case, the diode closes prematurely before we're fully done discharging the capacitor and before the PNP gate closes again. That means there would be a split second of big current flowing through the NPN base emitter junction. It's orders of magnitude less than the kiloamp simulation I showed before, and it's small enough and short enough in time that you don't have to worry about it if you really don't want to. But let's put a large-ish, let's say 20 kilo ohm resistor on the base of the NPN transistor and call it a day. As it stands now, we would sometimes have an oscillator and sometimes wouldn't. The reason is that the PNP transistor has a base emitter reverse breakdown voltage that is anywhere between 6 volts and 50 plus volts, and it's not something that we can really count on knowing until we actually put a transistor in and try it out. If the breakdown voltage is low, then we won't get a clean exponential curve as we charge the capacitor. Instead, there will be a huge rush of current at the very beginning, and then it'll look like a normal capacitor charge. That's not ideal. But there's an easy fix, and that's to put a general purpose diode in the way. The big trade-off is that our oscillator amplitude will be decreased. The bottom level is going to be a bit higher now, increased by the voltage drop of this additional diode, but it's worth it to not have to think about digging through our transistor pile to find one that works. One final easy improvement to this circuit is to replace the resistor with a constant current source, so that when we charge the capacitor, we do so at a constant voltage increase instead of an exponentially decaying one. Add a PNP transistor and connect the base of it to a voltage divider, which conveniently we already have one that we can use. We connect the emitter to the 12 volt rail via a 4 or 5 or whatever kilo ohm resistor to get approximately the same frequency we had with the 100 kilo ohm resistor before, but now the capacitor is going to charge at this nice constant rate and give us lovely sawtoothy triangles. In the next installment, if there ever is another installment, the logical thing to proceed with would be comparators and how to take this circuit and turn it into a square wave oscillator with ways to vary frequency and duty cycle. It's an Atari Punk console without a 555 timer, so that makes it more punk if you ask me, but I just made an electronics tutorial on triangles, so I am no authority on anything with punk in the name.